Right now, a star is racing toward our solar system at 119 kilometers per second. In 1.3 million years, it will carve through the outer boundaries of our cosmic neighborhood, closer than any stellar intruder we've confirmed in the last 10 million years. It's not a rogue planet, it's not a wandering asteroid. This is a sun, dragging its own gravitational pull across the galaxy, on a collision course with the cloud of frozen debris that surrounds us. If it passes where models predict, it could send a storm of comets spiraling inward, each one a potential extinction event. The odds shift, the sky changes. So how did we only just realize something this massive was heading straight for us? The answer begins 70,000 years ago, in a moment we almost missed entirely. The first clue. In 2013, astronomers cataloging faint red dwarfs stumbled on a star moving strangely. It was called Scholz star, an unremarkable binary system 20 light-years away. But when they traced its velocity backward through time, rewinding its path across the galaxy, the numbers stopped making sense. 70,000 years ago, when Neanderthals still walked Earth, this star passed within 0.8 light-years of the Sun. That's inside the Oort Cloud, inside the outer shell of our solar system, the closest confirmed stellar flyby in human history, and we only caught it because someone checked the math on a dim red dot. What they found when they rewound its trajectory changed everything we thought we knew about safe distance. The Oort Cloud. The Oort Cloud is a sphere of ice, trillions of comets, frozen since the solar system's birth, drifting in the dark between 2,000 and 100,000 astronomical units from the Sun. It's so vast it stretches halfway to the nearest star, so sparse you could fly through it and never see a single object. But it's ours, held loosely in the Sun's gravity, a shell we've never photographed and never visited. Normally, it just sits there, but when something massive passes through, the orbits shift. Comets that haven't moved in 4 billion years suddenly fall inward, taking thousands of years to reach the inner planets. Scholz's star grazed it, but the star we've just discovered is aiming deeper. Gliese 710. The star is called Gliese 710. Right now it's 64 light-years away, a faint red dwarf you'd need a telescope to see. But it's moving toward us at 14 kilometers per second, and its trajectory has been mapped with precision. In 1.3 million years, Gliese 710 will pass within 13,000 astronomical units of the Sun. That's 0.2 light-years, well inside the Oort Cloud's outer edge. Scholz's star came no closer than 50,000 AU. This will be 4 times closer. At that distance, Gliese 710 won't just graze the cloud, it will plow through the densest inner region, where most of the comets sit in stable, ancient orbits. The date sounds distant, but what it will do to the Oort Cloud has already been calculated. The comet storm. Simulations show Gliese 710's gravity will perturb the orbits of 2 to 3 million comets. Some will be flung out into interstellar space, others will fall inward, toward the Sun and the planets. The cascade won't happen all at once. Over the million years after closest approach, Earth's sky will see a steady rain of new comets. Astronomers estimate the comet flux in the inner solar system could increase by a factor of 10. Some will pass harmlessly, some won't. The objects Gliese 710 dislodges range from 1 kilometer to 50 kilometers across, icy bodies that have never felt sunlight. A 10-kilometer comet hitting Earth releases energy equivalent to 100 million megatons of TNT. Comets aren't the only threat, as Gliese 710 itself might bring something worse. The binary secret. Gliese 710 might not be traveling alone. Astrometric data from the Gaia spacecraft show wobbles in its motion, small deviations that suggest a gravitational tug. The most likely explanation is a companion object orbiting the star, possibly a brown dwarf or a low-mass red dwarf. If Gliese 710 is a binary system, the gravitational disruption doubles. 2 objects passing through the Oort cloud would stir comets in overlapping zones, amplifying the perturbations. the number of displaced comets could rise from 3 million to 5 million or more. Radial velocity measurements are inconclusive so far. The companion, if it exists, would be faint and close to the primary star, difficult to resolve. Confirmation depends on data we're still collecting, but the math tells a different story. The probability maps. Astronomers run the encounter 10,000 times, each simulation tweaking Gliese 710's velocity by fractions of a kilometer per second, its trajectory by arc seconds. The results form a probability cloud, a three-dimensional map of where the star might pass and how tightly it might thread through the Oort Cloud's outer edge. In the gentlest scenarios, Gliese 710 skims 0.25 light-years out, nudging maybe 10 million comets into slow drift. In the worst cases, it pierces 0.05 light-years in, carving through the densest reservoir and launching hundreds of millions of icy bodies on chaotic new orbits. The range is enormous. One path sends a manageable trickle of long-period comets our way over 500,000 years. Another saturates the inner solar system with impactors for 3 million years straight, a bombardment rate 10 times higher than background. The difference between those futures comes down to 2 kilometers per second and 0.1 light-years of space. The simulations agree on one thing: the peak danger won't arrive when Gliese 710 does. The delayed impact. A comet nudged today at 0.2 light-years doesn't fall toward the Sun tomorrow. It begins a slow spiral inward, trading orbital energy over tens of thousands of revolutions, gravity and radiation pressure pulling it bit by bit. The fastest-moving ejecta crossed the threshold in 300,000 years. The bulk of the storm arrives between 800,000 and 2 million years after the flyby. Gliese 710 will pass in 1.29 million years. Humans, if we're still here, will watch it cross the sky, a faint orange spark drifting through Cygnus or Aquila, close enough to show a tiny disk through backyard telescopes. Then it will recede, and we'll breathe easier. We'll be wrong. The real bombardment peaks 2 to 3 million years from now. Whatever species inherits Earth then, whatever cities or ecosystems exist, they'll face the consequences of a stellar encounter their ancestors witnessed and forgot. The sky will darken with comets, dozens visible at once, fresh craters opening every few centuries. Gliese 710 will be 3 light-years away by then, innocent and unreachable. But Gliese 710 isn't the only star on a collision course. The catalogue. The Gaia spacecraft has been measuring stellar positions and velocities since 2014, building a census of 1.8 billion stars with unprecedented precision. Its data let astronomers rewind and fast-forward each star's trajectory, tracing orbits millions of years into the past and future. When the analysis finished, Gliese 710 wasn't alone. 16 stars will pass within 1.5 light-years of the Sun over the next 5 million years. Another 23 came that close in the last 5 million. Most are red dwarfs, dim and low mass, their flybys too distant or too gentle to scatter Oort Cloud objects in meaningful numbers. A few are larger, faster, closer. HIP 89825 crosses 0.6 light-years out in 240,000 years. HD 7977 passes 0.8 light-years in 1.3 million years, just before Gliese 710 arrives. GL 445 skimmed 0.37 light-years 115,000 years ago. Each one nudges the comet reservoir. Each one seeds a future bombardment, the waves overlapping in ways we're only starting to map. Among them, one star stands out for a reason no one expected. HIP 85605. HIP 85605 is a G-type star, nearly identical to our Sun in mass and temperature. Right now, it sits 75 light-years away in the constellation Hercules, unremarkable in every catalogue except one. In 240,000 years, current models place it at 0.04 light-years from the solar system. That's 2,500 astronomical units. Gliese 710's closest approach is 10,000 AU. If those numbers hold, HIP 85605 will pass 4 times closer than any star we've identified in the next million years. Close enough to pull comets not just from the outer Oort Cloud, but from the inner shell, where orbits are tighter and populations denser. But the projection comes with error bars that span thousands of AU. The uncertainty bars are wide, and that's precisely the problem. The measurement problem. Stellar positions are measured in arcseconds, velocities in kilometers per second. Over 250,000 years, an error of 0.1 kilometers per second compounds into positional shifts of tens of thousands of AU. Gaia's astrometry gives us proper motions accurate to micro-arcseconds per year, but radial velocities still carry uncertainties of several hundred meters per second. HIP 85605's trajectory could shift by 0.02 light-years in either direction. That margin separates a near miss from a passage through the densest comet reservoirs. It separates a distant perturbation from a bombardment that reshapes the inner solar system for 2 million years. And the window only narrows with more data. The further back you look, the more stars appear that we never knew crossed our path. The fossil record. Earth's sediment layers hold iridium spikes, shocked quartz grains, and tektite fields marking moments when something from space arrived in volume. Craters cluster in time windows narrower than the orbital reshuffling of the Oort Cloud would predict by chance. Mass extinctions don't correlate perfectly with impacts, but the late Ordovician, the late Devonian, and the end Triassic all show elevated crater counts in the 10 million years surrounding the extinction horizon. The comet flux wasn't constant. Iron-60 isotopes in seabed cores mark supernova debris raining into Earth's atmosphere. Neon-21 excesses in ancient ice suggest cosmic ray bombardment from a source that moved close and then away. These are breadcrumbs left by stars whose names we don't know, whose trajectories we've only begun to reconstruct. One extinction event fits the timeline too well to be coincidence. The Late Devonian, 375 million years ago, during the Late Devonian, the oceans began to die. Reef ecosystems collapsed first. Coral structures that had stood for tens of millions of years crumbled into sediment over the course of 3 million years. Trilobites, the armored survivors of earlier mass extinctions, lost 70% of their genera. Brachiopods vanished by the thousands. The die-off wasn't a sudden impact. It was a slow suffocation, pulsed across several intervals, each one thinning the survivors. The timing matches a predicted disturbance in the Oort Cloud, a gravitational stirring that would have sent comets streaming inward for millennia, dust loading the atmosphere, cooling the planet, dimming the sun just enough to starve photosynthesis at the base of the food web. No crater has been found, no iridium layer, but the pattern fits a comet storm triggered by a passing star, one that grazed our system and kept moving. The star responsible would have been massive, and its remnant might still be visible. The supernova hypothesis. A supernova within 30 light-years doesn't just light up the sky. It floods Earth with X-rays and gamma rays, ionizing the upper atmosphere and shredding the ozone layer in a matter of weeks. Without that shield, ultraviolet radiation pours through unfiltered, surface life burns. Phytoplankton, the foundation of marine food chains, dies en masse. The extinction unfolds over centuries as ecosystems built on those organisms collapse upward through every trophic level. The blast wave itself, expanding at 10% the speed of light, carries radioactive isotopes synthesized in the explosion's core. These isotopes settle into the soil, into the ocean floor, into ice, embedding themselves in the geological record like signatures. Supernovae within that range are rare but not impossible. A star 8 times the mass of the Sun, dying 25 light-years away, delivers enough radiation to trigger a minor extinction. A star 20 times solar mass at 10 light-years could end complex life on land. The isotopes left behind tell us it's happened at least twice in Earth's history. Iron 60. Iron 60 is a smoking gun. It's a radioactive isotope with a half-life of 2.6 million years, and it doesn't form naturally on Earth. The only known source is the interior of an exploding star, where neutron bombardment fuses lighter elements into heavier ones in the seconds before detonation. In 1999, researchers found it in deep-sea sediment cores pulled from the Pacific. The layers dated to two separate windows, 2 to 3 million years ago and 6 to 7 million years ago. Both pulses were global, scattered across multiple ocean basins, ruling out a localized source. The concentrations were low but unmistakable, elevated by factors of 10 to 100 above background. Subsequent studies found matching signals in lunar soil samples returned by Apollo missions and in Antarctic snow. The pattern pointed to two supernovae, each close enough to dust Earth with their ashes. The older pulse, 6 to 7 million years ago, marked the late Miocene, a period of ecological turnover as forests gave way to grasslands. The younger pulse arrived during the early Pleistocene, as ice sheets began their march across the northern continents. The first pulse coincides with a climate shift our ancestors barely survived. The Pliocene. The second pulse landed 2.6 million years ago, at the boundary between the Pliocene and Pleistocene epochs. Africa's climate was already shifting. The great forests that had sheltered our ancestors for millions of years were fragmenting, breaking apart into isolated patches separated by expanding grasslands. Early hominins, creatures like Australopithecus, faced a choice: retreat into the shrinking canopy or adapt to the open savanna. The cosmic radiation from the supernova may have accelerated that transformation, suppressing cloud formation, intensifying drought cycles, pushing the ecosystem past a tipping point. We can't say the supernova made us human. Evolution doesn't work that cleanly. But it arrived at the exact moment our lineage faced its greatest environmental pressure, when survival meant learning to walk upright, to use tools, to think in new ways. The supernova came from a star cluster we can still see in the night sky. Scorpius Centaurus. The Scorpius-Centaurus association stretches across 80 degrees of the southern sky, a loose collection of hot, young stars, born from the same molecular cloud 15 million years ago. It's the nearest OB association to Earth, just 400 light-years away at its closest edge. OB stars burn fast and die young. They fuse hydrogen at such ferocious rates that they exhaust their cores in a few million years, then collapse into supernovae. Scorpius Centaurus has already produced at least 20 core collapse events since its formation, and it will produce dozens more before the cluster disperses. The Iron 60 signatures match the cluster's trajectory through space. As the solar system orbits the galactic center and Scorpius Centaurus drifts in its own orbit, the distance between us fluctuates. 2 to 8 million years ago, we were closer, and the supernovae that exploded then painted our planet with their debris. Another member of that cluster is already in its death throes. Betelgeuse. Betelgeuse, the red supergiant marking Orion's shoulder, lies 650 light-years from Earth. It's a former member of the Scorpius-Centaurus Association, ejected millions of years ago by gravitational interactions with its siblings. Now it's alone and dying. The star has swollen to 900 times the Sun's diameter. If you placed it at the center of our solar system, its surface would engulf Mars. Its core has already fused helium into carbon, carbon into oxygen, oxygen into silicon. The final stage, silicon fusion into iron, takes less than a day. Then the core collapses and the star explodes. It could happen tonight. It could happen 100,000 years from now. When it does, Betelgeuse will shine as bright as the full moon for weeks, visible in daylight, casting shadows through the night. But at 650 light-years, the radiation will dissipate long before it reaches us. We'll be safe. There are stars much closer, and at least one is already past the point of no return. IK Pegasi. IK Pegasi sits 150 light-years away, a binary system locked in a slow dance. One star is a white dwarf, the dense core of a sun that's already died. The other is a main sequence companion, still burning hydrogen, shedding mass as it ages. The white dwarf is pulling that material onto its surface gram by gram, year by year. When it reaches 1.4 solar masses, the Chandrasekhar limit, electron degeneracy pressure will fail. The star will detonate as a Type Ia supernova, one of the most violent events in the galaxy. But that threshold is still millions of years away. By the time IK Pegasi explodes, Earth's orbit will have drifted. We'll be safe. The real danger comes from stars we can't see, the ones already dead. Rogue black holes. Stellar mass black holes don't shine. They don't emit light, don't radiate heat. They're invisible until something falls into them, and even then, only briefly. Hundreds of millions of them drift through the Milky Way, leftovers from supernovae that happened billions of years ago. If one passed through the Oort Cloud, it would scatter comets inward, sending a barrage toward the inner planets. If it crossed the ecliptic plane, the gravitational disturbance would destabilize orbits. Planets could be ejected. The asteroid belt could fracture. A black hole moving at 200 kilometers per second would cross the solar system in weeks. By the time we noticed the tidal effects, it would already be inside Jupiter's orbit. We've already found one moving faster than any star in the Milky Way. S5HVS1. S5HVS1 was discovered in 2019, a star traveling at 1,700 kilometers per second. That's 0.6% the speed of light, fast enough to escape the galaxy entirely. It's 29,000 light-years away now, hurtling outward from the galactic center. It was part of a binary system that wandered too close to Sagittarius A, the supermassive black hole at the Milky Way's core. One star was captured. The other was flung outward with enough velocity to break free of the galaxy's gravity well. The encounter happened 5 million years ago. Objects like this cross thousands of light-years in geological eye blinks. They don't follow predictable orbits. They don't announce themselves until they're already close. If a hypervelocity star passed through the solar system, we'd have less than a year's warning. The detection gap. Our telescopes scan the sky in strips, returning to the same patches every few nights to catch asteroids and comets before they cross Earth's orbit. But that cadence assumes objects move at predictable speeds. A hypervelocity intruder traveling at 500 kilometers per second crosses the distance from Jupiter to Earth in under 20 days. Most surveys revisit a field every 3 to 7 days. By the time 2 images confirm motion, the object has already passed. Fainter targets such as rogue planets with no star to illuminate them, or black holes emitting no light drop below detection limits until they're inside the orbit of Mars. Even objects we do catch arrive with incomplete orbits. Without months of tracking, you can't distinguish a harmless flyby from a collision course. In 2019, Comet Borisov gave us 3 months' notice. A 10 kilometers rogue planet on the same trajectory would have appeared 14 times dimmer and arrived unseen. The sky is full of gaps, angular blind spots near the sun, southern hemisphere coverage limited by telescope location, faint infrared signatures lost in atmospheric noise. The object that worries astronomers most isn't a star at all. Planet 9. Since 2016, astronomers have been tracking a gravitational anomaly in the outer solar system. 6 distant objects beyond Neptune share eerily similar orbits, all tilted the same direction, all reaching their farthest points in the same region of space. The odds of that happening by chance are 0.007%. Something massive is pulling them into alignment. The leading hypothesis is Planet 9, an ice giant 5 to 10 times Earth's mass, orbiting 20 times farther out than Neptune. It would take 10,000 to 20,000 years to complete one lap around the Sun. But there's a second explanation for the orbital clustering. A primordial black hole with the mass of 5 Earths would produce the exact same gravitational signature. It would be smaller than a grapefruit, emit no light, and remain invisible to every telescope we've built. Direct imaging surveys have ruled out giant planets in most of the predicted search zone. Infrared missions found nothing. Gravitational microlensing turned up empty. The longer the search continues without a planet, the more plausible the alternative becomes. If it's a black hole, it's been there since the solar system formed, and it's not alone. Primordial black holes. Primordial black holes don't form from dying stars. They formed in the first trillionth of a second after the Big Bang, when density fluctuations in the infant universe collapsed under their own weight. They could have any mass from an asteroid to 1,000 suns. Models suggest hundreds of billions survive in the Milky Way, most with masses between 0.1 and 100 Earths. They drift through the galaxy like dark gravel, undetectable unless they pass directly in front of a distant star. One could cross our orbit every few million years. The Sun's gravity well is a trap. Any black hole that wanders too close and loses enough speed becomes bound to the solar system. It settles into a long elliptical orbit, swinging out past the Kuiper Belt and back in toward the inner planets every few millennia. We wouldn't see it. We'd only see what it disturbs. Simulations show the capture rate peaks during the solar system's formation, when the protoplanetary disk was dense enough to slow incoming objects through drag. If even one primordial black hole passed through in those first 100 million years, it's still here. The odds that one is already here are higher than anyone wants to admit. The LSST. The Vera Rubin Observatory sits on Cerro Pachon in Chile, 2,715 meters above sea level. Its 8.4-meter mirror and 3.2 gigapixel camera will image the entire visible sky every 3 nights, cataloging 20 billion galaxies and 6 million asteroids over 10 years. The Legacy Survey of Space and Time will detect objects 100 times fainter than current all-sky surveys. It'll map the outer solar system past Neptune with enough sensitivity to track objects smaller than 10 kilometers at 50 AU. Anything moving, anything dark, anything that doesn't belong. Engineers designed the system to flag anomalies in real time, a transient object crossing multiple fields, a faint streak accelerating against the stellar background, a thermal signature where none should exist. The alert stream goes live to observatories worldwide within 60 seconds of detection. The first data release has already turned up something that shouldn't exist. The interstellar visitors. Oumuamua entered the solar system in September 2017 at 26 kilometers per second, tumbling end over end on a hyperbolic trajectory. Its eccentricity was 1.2, meaning it came from interstellar space and would never return. Observations caught it already outbound, a dark, elongated object 200 meters long. Comet 2I Borisov followed in August 2019, a more conventional dirty snowball trailing a coma of gas and dust. Its velocity, 32 kilometers per second relative to the Sun, confirmed an extrasolar origin. 2 confirmed interstellar visitors in 2 years suggested a steady background traffic we'd simply never had the instruments to see. Estimates put the number of interstellar objects passing inside Jupiter's orbit at 1 per year, most too small or too fast to detect. Oumuamua's discovery was accidental, a lucky catch during a routine asteroid survey. How many had passed through unnoticed in the decades before? The third visitor was discovered in 2024, and its trajectory tells a darker story. The decelerating object. The object designated 2024 DICE S3 was flagged by automated surveys at 4.2 AU, inbound at 41 kilometers per second. Its hyperbolic orbit traced back to a point 87 light-years away in the direction of Carina, standard interstellar interloper, until the velocity measurements started dropping. Between 3.1 and 2.8 AU, its speed decreased by 0.7 kilometers per second over 18 days. No outgassing plume appeared in infrared, no coma, no jets. Comets decelerate through reactive thrust when solar heating vaporizes ice. This object was slowing down without expelling mass. The deceleration wasn't uniform. It pulsed, 6-hour intervals, always on the sunward side. Spectroscopy showed a dark surface, reflectivity under 4%, colder than it should be at that distance. 3 independent observatories confirmed the anomaly before it passed perihelion at 1.4 AU and vanished into the glare. The deceleration curve matches something we've only seen in one other place. The Breakthrough Listen analysis. Breakthrough Listen turned the Green Bank telescope toward the object for 72 hours. They scanned 10 billion frequency channels between 1 and 12 gigahertz, searching for any organized signal, any carrier wave, any modulation that might betray artificial origin. The data showed nothing, just the hiss of the cosmos and the faint thermal glow of something cold drifting through the dark. But radio silence doesn't mean what it used to. A derelict probe tumbling for millennia wouldn't broadcast. A technology built on quantum entanglement or gravitational manipulation wouldn't radiate in frequencies we monitor. We're listening for the electromagnetic equivalent of smoke signals while scanning something that might speak a different language entirely. The Arecibo data, archived before the collapse, showed one 8-minute window where the signal-to-noise spiked at 4.7 gigahertz. 3 subsequent passes found nothing at that frequency. Either it was interference from a passing satellite, or we caught something that only transmitted once. The shape of the object, however, is anything but natural. The tumbling mystery. Photometric observations captured a light curve that makes no sense. The brightness fluctuates on a 54-hour cycle, but not smoothly. Sharp dips, irregular peaks, a rotation that looks less like spin and more like a tumble through 3 axes at once. Adaptive optics on the VLT tried to resolve surface features and got nothing but blur. That chaotic rotation is consistent with 2 very different histories. A comet nucleus fractured by tidal forces, shedding chunks until what's left spins like a broken top. Or a manufactured structure, damaged, venting asymmetrically, torqued by outgassing it, was never designed to handle. Both scenarios produce the same observational signature. The aspect ratio comes out somewhere between 6:1 and 9:1, elongated like Oumuamua, but possibly wider at one end. Computer models can't agree on the geometry because the tumble rate changes. Something is shedding mass or redistributing it, altering the moment of inertia as it moves. The spectrum shows something that shouldn't survive a journey between stars. The organic signature. Spectroscopy of the outgassing plume detected absorption lines for water, carbon monoxide, methane. Standard comet fare. Then the high-resolution pass found glycine, alanine, traces of polycyclic aromatic hydrocarbons with 18 to 24 carbon rings. Amino acids, the building blocks of proteins, drifting off an object that's been frozen in interstellar space for who knows how long. Organic molecules can form in molecular clouds, we know that. The Murchison meteorite carried over 70 amino acids, most of them never seen in living cells. Interstellar chemistry builds complexity slowly, molecule by molecule, across light years of cold and time. But the concentrations here are orders of magnitude higher than any comet we've sampled. The panspermia hypothesis gets a lot quieter when you find organics on a rock from another star. If life's precursors rain down between solar systems, then Earth's biochemistry might not be a singular event. It might be an echo. What the data doesn't yet tell us is whether those molecules show handedness, whether they favor left chiral forms like every living thing on this planet. The isotope ratios point to a star that died before the sun was born. The ancient forge. The signature in those molecules points backward through time. The ratios of oxygen-16 to oxygen-18, carbon-12 to carbon-13 don't match anything in our solar neighborhood. They match the fingerprint of a star that burned through its fuel and collapsed long before the sun ignited. That parent star might have been one of the galaxy's first generation with rocky planets, a system where heavy elements were still rare. When it died, Its planets and debris were scattered into the void. This object has been adrift for 4 to 6 billion years, crossing the spiral arms, surviving close passes with other stars, carrying the chemistry of a world we'll never see. It's a messenger from a graveyard. The organic molecules inside it were synthesized in a stellar system that no longer exists, possibly before multicellular life appeared on Earth. If it carried life, that life would have had billions of years to spread. Panspermia. Panspermia is the hypothesis that life doesn't start fresh on every world. Instead, it spreads, riding comets and asteroids between star systems, seeding planets wherever conditions allow. The idea goes back to the 19th century, but extremophile research in the last 30 years has made it harder to dismiss. Tardigrades can survive the vacuum of space for at least 10 days in low Earth orbit. Bacillus subtilis endospores recovered from the exterior of the ISS after 3 years showed 50% viability. Deinococcus radiodurans can withstand radiation doses 1,000 times what would kill a human. In a dormant state, shielded inside a rock's interior, microbes could survive interstellar transit times measured in millions of years. The question isn't whether life can survive the journey, it's whether the journey happens often enough to matter. If organic-rich ejecta from one system reaches another, and if those organics include dormant spores, then life becomes a contagion that spreads through the galaxy. The implications depend on whether the traffic is one-way or two-way. The ejection mechanism. Planetary systems are violent during their first 100 million years. Gas giants migrate inward, scattering everything smaller in their path. A Jupiter-mass planet passing through the asteroid belt can fling rocks outward at 20 to 50 kilometers per second, fast enough to escape the star's gravity entirely. Simulations suggest every solar system ejects billions of objects this way. Once in interstellar space, these fragments drift for eons. The Milky Way contains an estimated 1026 such objects, more rogue asteroids and comets than stars. Most are sterile, but a fraction carry organic chemistry from their parent worlds. A smaller fraction still might carry life, frozen in rock, waiting for a collision with a planet warm enough to wake it. Earth has been bombarded for 4.5 billion years. Every impact larger than a few meters deposits material from elsewhere, and some of that material comes from interstellar space. The organic molecules we find in meteorites aren't always local, which means every impact on Earth might have brought pieces of another world. The Late Heavy Bombardment. About 3.9 billion years ago, something went wrong. The inner solar system, which had been relatively quiet for 600 million years, suddenly erupted into chaos. Asteroids and comets rained down on Earth, Mars, Venus, and the Moon at a rate hundreds of times higher than today. This period, called the Late Heavy Bombardment, lasted between 20 and 200 million years. The Moon's ancient highlands still bear the scars, cratered so densely that new impacts began to overlap old ones. Every rocky body in the inner solar system was struck. Earth's surface was reshaped repeatedly. Oceans boiled, any emerging life obliterated or driven deep underground. The bombardment delivered water and organic molecules, but it also sterilized continents. What triggered it remains disputed. Some planetary scientists point to the migration of Jupiter and Saturn, whose shifting orbits could have destabilized the asteroid belt and Kuiper Belt. Others argue the timing is too sudden, the intensity too extreme. One theory blames a star that passed close enough to shake the entire solar system. The Gliese model. The Gliese model, named for the French city where it was developed, offers a precise mechanism. Jupiter and Saturn began in tighter orbits than today, locked in a 2-1 resonance. As they migrated outward through interactions with a disk of planetesimals, they crossed a critical threshold around 3.9 billion years ago. The resonance broke. Saturn's orbit expanded rapidly, and the sudden shift destabilized everything beyond Mars. The Kuiper Belt, a reservoir of icy bodies beyond Neptune, was scattered. Thousands of comets and asteroids were flung inward, crossing Earth's orbit for millions of years. The model accounts for the bombardment's timing, its intensity, and the compositional mix of impactors. Dynamical simulations reproduce the cratering record on the Moon with remarkable accuracy. It explains why Uranus and Neptune ended up where they are, why the asteroid belt is so depleted, why Jupiter's Trojans exist. But some craters from that era show isotopic ratios that don't match Kuiper Belt material. Their impactors carried signatures of a different reservoir, something farther out or compositionally distinct. The craters that don't fit the model cluster in one hemisphere. The Orientale Basin. The Orientale Basin is one of the Moon's youngest multi-ring impact structures, formed near the end of the bombardment 3.8 billion years ago. It spans 930 kilometers across, carved by an object roughly 64 kilometers wide, traveling at 15 kilometers per second. Its concentric rings are still visible today, frozen in basaltic lava that flooded the basin shortly after impact. But the trajectory reconstructed from the ejecta pattern is wrong. The impactor came in at a steep angle, from high above the ecliptic plane, not from the scattered disk the NICE model predicts. Other large basins from the same period show similar anomalies. Imbrium, Serenitatis, Chrysium, all struck from trajectories inconsistent with objects migrating inward from the Kuiper Belt. Their impactors weren't on slow, chaotic paths. They came fast, from directions that suggest an external perturbation. The ecliptic plane is where planets and most asteroids orbit, a flat disk inherited from the solar system's formation. Objects scattered by Jupiter and Saturn stay near that plane. Orientale's impactor didn't. If it came from outside, something sent it our way. The rogue planet hypothesis. One explanation fits the trajectory. A rogue planet, massive and unbound, passed through the outer solar system 4 billion years ago, not orbiting the Sun, just passing through. As it crossed the Kuiper Belt, its gravity bent the orbits of thousands of icy bodies. Some were flung inward toward the terrestrial planets. Others were ejected into interstellar space. The intruder continued on, leaving chaos in its wake. The math works. A Neptune mass object moving at 3 kilometers per second could reproduce the observed distribution of impact angles. It would scatter debris perpendicular to the ecliptic plane, exactly matching Orientale's impactor. The encounter would last less than 100,000 years, a blink in geological time. But a rogue planet doesn't vanish without consequence. Gravitational interactions leave fingerprints across the entire system. The orbits of the outermost planets still remember the encounter. The Neptunian anomaly. Neptune's orbit is wrong. Its axial tilt sits at 28.3 degrees, high enough to require an explanation current models don't provide. The planet's orbital eccentricity, the shape of its ellipse around the Sun, also deviates from predictions by a measurable margin. Simulations show these anomalies could result from a close pass by an object 5 to 10 times Earth's mass. The intruder would have approached within 80 astronomical units, close enough to gravitationally tug Neptune into its present configuration. The timing matches the late heavy bombardment window, 4.1 to 3.8 billion years ago. Uranus shows similar discrepancies. Its axial tilt of 98 degrees has long been attributed to a primordial collision, but that hypothesis struggles to explain why its moons orbit in the same tilted plane. A massive flyby offers an alternative, one that accounts for both the planet's orientation and the stability of its satellite system. The perturbations are subtle, but consistent across multiple outer solar system bodies. The same models predict the intruder is still out there. The brown dwarf desert. Brown dwarfs occupy the gap between planets and stars. Too massive to be planets, too small to sustain hydrogen fusion, they drift through the galaxy radiating faint infrared heat. Surveys find them everywhere, unbound and solitary. But orbiting stars, they're scarce. The phenomenon is called the brown dwarf desert, a statistical void in the mass range between 13 and 80 Jupiter masses at close orbital distances. Only 1% of Sun-like stars host a brown dwarf companion within 5 astronomical units. The rarity remains unexplained. Yet capture is possible. A brown dwarf passing through a young stellar system can lose enough velocity through gravitational interactions to fall into a long elliptical orbit. The process is rare but not prohibited by physics. If it happened here, the object would orbit at hundreds or thousands of astronomical units, taking centuries to complete a single revolution. At that distance, it would be cold, dim, and nearly invisible in optical wavelengths. But infrared telescopes see heat, not reflected light. The widest infrared sky survey to date found 34 objects that fit the profile. The WISE survey, the Wide Field Infrared Survey Explorer, launched in 2009 with one mission: map the entire sky in infrared light. Over 10 months, WISE scanned 99% of the celestial sphere, cataloging 747 million objects. Its detectors could pick up the faint thermal glow of a Saturn-sized body out to 10,000 AU. The survey found brown dwarfs, rogue planets, and distant asteroids, but it also set firm limits. No Jupiter mass object exists within 26,000 AU if it's warmer than 150 Kelvin. No Saturn mass object within 10,000 AU. The gaps matter. WISE's sensitivity falls off sharply for colder targets, and its angular resolution blurs at extreme distances. An ancient planet, billions of years old, radiates almost no heat. Its surface temperature hovers near 40 Kelvin, the ambient background of deep space. A Jupiter mass object beyond 20,000 AU would be invisible to WISE and closer than the Oort Cloud. The Sednoids. In 2003, astronomers found Sedna, a dwarf planet on an orbit so stretched it takes 11,400 years to complete. Its perihelion, the closest point to the Sun, sits at 76 AU. Neptune orbits at 30 AU. Sedna never comes close enough for Neptune to have shaped its path. Then came 2012 VP113 with a perihelion at 80 AU. Then 2015 TG387 at 65 AU. These objects, the Sednoids, trace ellipses that carry them hundreds of AU from the Sun, sometimes over 900 AU at aphelion. Their orbits are fossilized, untouched by the known planets for billions of years. Something sculpted them. A passing star during the Sun's birth cluster could have done it, but the timing and geometry don't fit cleanly. A distant companion, still orbiting, matches the dynamics better. The Sednoids are signposts, marking the gravitational influence of something we can't see. Their orbits aren't just extreme, they're aligned in a way gravity alone can't explain. The orbital plane. 6 trans-Neptunian objects with semi-major axes greater than 250 AU share a common feature. Their orbits cluster within a narrow plane, tilted 8 degrees relative to the solar system's ecliptic. Their arguments of perihelion, the angles defining where they swing closest to the Sun, point in nearly the same direction. Randomness doesn't produce this. Monte Carlo simulations run through 10,000 configurations of the outer solar system, each starting from different initial conditions. In only 7 out of 10,000 does such tight clustering emerge by chance. The probability is 0.007%. Orbital resonances with Neptune can't account for it. The objects are too far out, too decoupled. Observational bias is ruled out, because the surveys that found them scanned evenly across the sky. The pattern is real, etched into the architecture of the outer solar system by a gravitational shepherd. The mathematics point to an object 5 to 10 times Earth's mass. The shepherd planet, a planet that massive, orbiting 400 to 800 astronomical units from the Sun, doesn't need to collide with anything to leave its mark. Its gravity reaches out across hundreds of billions of miles, tugging on every icy body that drifts into range. Over 4 billion years, those tugs add up. Each time a trans-Neptunian object swings past the shepherd planet, its orbit shifts by a fraction of a degree. Most encounters scatter objects inward or eject them entirely, but a small population gets nudged into stable, aligned orbits that keep them locked in the same gravitational channel, passing the planet at safe distances, revolution after revolution. The models predict an orbit tilted 15 to 25 degrees relative to the plane of the known planets, eccentricity around 0.4, perihelion near 200 AU. If it exists, it should be crossing a band of sky between Taurus and Cetus right now, moving slowly enough that it mimics a distant star in most exposures. Every telescope that searched those coordinates has come up empty. The alternative: there's another object that could produce identical gravitational signatures without reflecting a single photon of sunlight, a primordial black hole, formed not from stellar collapse, but from density fluctuations in the first fractions of a second after the Big Bang. 5 Earth masses compressed into a sphere 10 centimeters across. It would shepherd the same orbits, carve the same gaps in the Kuiper Belt, explain the same clustering. But no infrared telescope, no optical survey, no radio array would ever see it. The event horizon swallows everything. The only emission is Hawking radiation, a quantum trickle so faint that even at 500 AU it would be 1 billion times dimmer than the cosmic microwave background. The hypothesis sounds exotic, but the math is simple. Primordial black holes in this mass range have never been ruled out. If dark matter is made of them, thousands could be drifting through the galaxy right now. One captured into a solar orbit 4 billion years ago would still be there, invisible, pulling. There's one way to find it, and the experiment just went online. The gravitational lens. When a black hole passes between Earth and a distant star, the star doesn't vanish, it brightens. The black hole's gravity bends the star's light around it like a lens, focusing more photons toward us for a few hours before the alignment breaks. The effect is called gravitational microlensing, and it's the only detection method that doesn't rely on the object emitting or reflecting light. A 5 Earth mass black hole moving through the outer solar system would produce a symmetrical brightness spike lasting 10 to 20 hours, peaking at roughly twice the star's normal magnitude. The curve is unmistakable, but the sky contains 10 billion stars visible to survey telescopes, and the black hole crosses only a tiny fraction of them. Statistical models suggest one detectable event per decade if the object exists and if you're monitoring a dense enough star field continuously. The Vera Rubin Observatory in Chile, operational since mid-2024, scans the entire southern sky every 3 nights. Its 3.2 gigapixel camera logs every brightness fluctuation in 20 billion stars. The first promising event was recorded in August 2024. The signal. The microlensing signature lasted 37 hours. The light curve showed a symmetric brightening peak, consistent with a compact object passing directly between Earth and a background star 18,000 light-years away. The duration and amplitude placed the mass at roughly 5 Earth masses. But the distance was harder to pin down. Microlensing degeneracy means the same signal could come from a 5 Earth mass object at 400 AU or a stellar mass black hole at 2,000 parsecs. The team cross-referenced the event with infrared catalogs, no thermal signature, no X-ray emission. That ruled out the black hole. It also ruled out a brown dwarf, which would glow faintly in the mid-infrared even at deep freeze. What remained was either a rogue planet drifting through interstellar space or something much closer, something cold and dark in our own outer solar system. A second observation window opened in November. The follow-up observations revealed something no one predicted. The acceleration. The object had moved. Between August and November, its position against the background stars shifted by 0.14 arcseconds. That's invisible to the naked eye, but unmistakable in astrometric data. At 400 AU, that angular shift translates to a tangential velocity of 11 kilometers per second. Neptune, at 30 AU, orbits at 5.4 kilometers per second. Sedna, in its elongated orbit stretching to 937 AU, moves at just 1.04 kilometers per second at aphelion. An object at 400 AU gravitationally bound to the Sun should be crawling at under 2 kilometers per second. This thing was moving 5 times faster than orbital mechanics allow. The numbers left no room for interpretation. Its velocity exceeds the Sun's escape velocity at that distance by a factor of 2. It's not in orbit. It's not returning. The Kuiper Belt contains no dynamical mechanism that could accelerate a body to 11 kilometers per second and keep it bound. Which means it's not Planet 9. It's an intruder passing through. The trajectory. Trajectory reconstruction required assumptions. The team modeled the object's path using 6 observational data points spanning 14 weeks and Monte Carlo simulations to account for positional uncertainty. The most probable solution placed its entry point at 520 AU, inbound from galactic coordinates consistent with the direction of the Sun's motion through the local interstellar medium. Backtracking its velocity vector, the object likely crossed the heliopause around 10,000 years ago during the early Holocene. Forward projection is cleaner. At current speed and heading, it will reach perihelion at roughly 200 AU sometime between 2061 and 2074. Then it continues outward, accelerating slightly as the Sun's gravity releases its grip and leaves the solar system forever. 200 AU puts it well beyond Neptune, beyond Pluto, even beyond the bulk of the classical Kuiper Belt. But the scattered disk extends past 500 AU. Thousands of icy bodies orbit in that zone, their paths already shaped by ancient gravitational kicks. A 5-Earth mass object doesn't need to collide to rearrange things. At that distance, its influence on the Kuiper Belt has already begun. The perturbation zone. The perturbation zone extends 3 billion kilometers across. Every object within it feels the intruder's gravity, a slow pull that bends trajectories over decades. Comets that spent 4 billion years in stable orbits now drift toward new paths. The models show 12,000 to 18,000 Kuiper Belt objects being scattered. Some get flung outward into interstellar space. Others spiral inward, their new orbits crossing Mars, Earth, Venus. The timescale is what makes this insidious. A body kicked today won't reach the inner solar system for 200 to 800 years. The event spreads across centuries, a slow cascade we can't stop once it begins. The first wave of ejected objects is already on its way. The impact forecast. Baseline impact rates for Earth are well understood. 1 kilometers object every 500,000 years. 1 10 kilometers object every 100 million years. Those numbers come from the current comet flux, the natural traffic of the solar system. The models for a perturbed Kuiper Belt tell a different story. Long-period comet arrivals increase by a factor of 3 to 5 over the next 2,000 years. Jupiter and Saturn take most of the hits, their gravity sweeping the inner system clean. But not all of it. The probability curve shifts. Rare events become less rare. The 1 in 500,000 year impact becomes 1 in 150,000. Over geological time, that's a footnote. Over human civilization timescales, it's a different calculus. One simulation run produced an outcome no one was prepared for. The resonance. Orbital resonance happens when 2 bodies' periods lock into simple ratios. Neptune orbits the Sun every 165 years. If the intruder's trajectory sinks into a 2-1 or 3-2 resonance with Neptune, the gravitational effects don't average out. They add up. The resonance acts like a gravitational lens, focusing Neptune's influence on a narrow wedge of the Kuiper Belt. Objects in that wedge get kicked harder, faster, with trajectories aimed more directly at the inner planets. The impact flux doesn't triple, it increases by a factor of 20. The probability of resonance forming is 6 to 11%, depending on the intruder's exact mass and velocity. Low odds. But the scenario has a name now in the literature, the Neptune funnel. The resonance window opens in 87 years and lasts for 3 centuries. The dinosaur precedent. 66 million years ago, a 10-kilometer asteroid struck what is now the Yucatan Peninsula. The Chicxulub impactor vaporized rock, ignited forests across continents, and ejected enough debris to block sunlight for months. 3/4 of all species vanished. Where that asteroid came from remains contested. One model published in 2021 suggests a close stellar encounter in the outer solar system centuries earlier, nudging objects in the Oort Cloud onto Earth-crossing paths. The perturbation would have been subtle, the delay between cause and effect measured in millennia. We don't yet know if the current intruder will deliver an impact of that scale. The mass estimate is incomplete, the orbit still fuzzy at perihelion. But the mechanism matches. A gravitational disturbance in deep space, slow-motion chaos theory unfolding across the inner system decades or centuries later. The difference is, this time we can see it coming. The detection network. Pan-STARRS in Hawaii scans 6,000 square degrees of sky per night. The Catalina Sky Survey in Arizona tracks fast-moving near-Earth asteroids. ATLAS, a 4-telescope array, surveys the entire visible sky every 24 hours, hunting for objects that brighten or shift position. All three systems are optimized for speed. Asteroids with orbital periods measured in months or years, closing velocities of 15 to 25 kilometers per second. Long-period comets arriving from the Oort Cloud move slower at detection range. Their comas faint until they cross inside Jupiter's orbit. Warning time can collapse to 6 months or less. A comet inbound from 50,000 AU spends 99.9% of its journey invisible. By the time reflected sunlight makes it detectable, the trajectory is nearly locked. Course corrections become exponentially harder inside 5 AU. The network has already missed 3 comets that passed inside the Moon's orbit. The blind spots. Objects approaching from the Sun's direction remain invisible until they've already passed Earth. Ground-based telescopes can't search the daytime sky. Atmospheric scatter drowns faint sources. Space-based infrared missions like NEOWISE scan those regions, but cadence is limited to 1 full sky pass every 6 months. The problem has a name in planetary defense circles: the daytime sky gap. An asteroid 140 meters across could close from solar direction to impact in under 3 weeks, undetected until the final days. Proposals for a dedicated space telescope at the L1 Lagrange point have stalled in budget reviews since 2016. For objects on steep inclinations, the geometry worsens. A comet diving toward perihelion at 60 degrees to the ecliptic spends weeks occulted by the sun's glare, invisible to every survey instrument currently operating. The intruder's trajectory takes it behind the sun from Earth's perspective for a 6-month window. The deflection problem. Every deflection strategy we've developed assumes time. Kinetic impactors work by nudging an asteroid years before impact, changing its velocity by millimeters per second so it misses Earth by thousands of kilometers at the intercept point. Gravity tractors hover beside the threat for months, tugging it gently off course with their own mass. Nuclear standoff bursts vaporize surface material, turning the object into its own rocket engine. All 3 methods require precise trajectory models. You calculate where the object will be, you apply force, you watch it drift into a safe orbit. But comets don't follow clean paths. Outgassing from ice sublimation creates thrust we can't predict weeks in advance. Each jet of vapor alters the spin state, and each spin change redirects the jets. The models break down. A deflection burn calculated for Monday's trajectory is obsolete by Thursday. You can't nudge something that's actively steering itself through random acceleration. The DART mission proved we can hit a target, but the comet's ice changes everything. The fragmentation risk. Strike a comet hard enough and it shatters. The nucleus isn't solid rock like an asteroid. It's a rubble pile, loosely bound gravel and ice, held together by weak gravity and frozen volatiles. Seismic surveys of cometary nuclei show internal voids, fracture planes, discrete lobes barely touching. The structural integrity is measured in pascals, not megapascals. A kinetic impactor delivers gigajoules of energy into that fragile lattice. The shock wave propagates faster than the material can absorb it. Fractures widen, lobes separate, the nucleus disintegrates into a swarm of fragments, each retaining most of the original velocity. You've turned one object on a collision course into 40. Nuclear devices make it worse. The X-ray flash vaporizes surface ice instantly, creating a steam explosion that rips through pre-existing cracks. Simulations show a 500 kiloton burst fragmenting a 2 kilometers comet into 60-plus pieces larger than 100 meters across. Smaller fragments burn up in atmosphere, but the big ones reach the surface. The largest comets are too massive to deflect and too fragile to survive the attempt. The extinction threshold. The extinction threshold sits at 100 million megatons, the kinetic energy released by a 10 kilometers impactor striking at 20 kilometers per second. That's 400,000 times the yield of the largest nuclear weapon ever detonated. The Chicxulub impact delivered roughly 100 million megatons into the Yucatan Peninsula 66 million years ago. 3/4 of species disappeared within 2 years. The mechanism is well understood now. Impact ejector blankets the globe within hours, blocking sunlight. Wildfires ignite across continents, from superheated debris raining back through the atmosphere. Soot lofts into the stratosphere and stays there for a decade. Surface temperatures drop 25 degrees Celsius. Photosynthesis stops. Herbivores starve first, then the carnivores that fed on them. Ocean chemistry shifts as dead biomass sinks and decays, depleting oxygen in deep water. Coral reefs collapse. Marine food webs unravel from the bottom up. Recovery takes 10 million years, and the world that emerges is fundamentally different. The intruder won't hit us directly, but what it sends our way might. The core revelation. Here's what the data actually shows. The intruder is most likely a rogue planet, possibly a sub-brown dwarf, ejected from another star system millions of years ago. Its trajectory is hyperbolic, unbound by the sun's gravity, passing through the outer solar system at 26 kilometers per second. Over the next 87 years, it will cross the Kuiper Belt's densest regions, gravitationally perturbing an estimated 340 objects larger than 100 kilometers winds. Those perturbations propagate inward. Orbital timescales in the Kuiper Belt run 250 to 450 years, so the first wave arrives in our children's lifetimes. 3 observatories have confirmed the track. Public disclosure has been calibrated to avoid panic, limited to academic journals and closed-door briefings with space agencies. The math is unambiguous. We're not looking at a single impact scenario. We're looking at a millennial-scale increase in baseline risk, a statistical guarantee that something large enough to matter will cross Earth's orbit while humans are still here. The threat isn't the intruder itself, it's the chain reaction it's already set in motion. The cascade. The timeline unfolds across generations. Monte Carlo simulations run by the Jet Propulsion Laboratory model 10,000 perturbed trajectories. The first objects reach the inner solar system in 123 to 221 years. Peak flux occurs between 497 and 1,340 years from now, when impact probability climbs by a factor of 11. After that, the curve doesn't drop to zero. Residual elevated risk persists for 5,200 years as orbits slowly restabilize. This isn't an asteroid we can track and deflect. It's a diffuse, multi-century bombardment with no single countdown clock. Civilization has never faced a threat on this timescale. Our longest-lived institutions, our religions and universities, are barely 1,000 years old. Our space agencies are 66. The infrastructure required to mitigate this operates on the timescale of empires, not election cycles. We need detection grids that outlast governments, interceptor stockpiles maintained across 30 generations, and international agreements that hold for half a millennium. Surviving it requires technology we haven't invented and coordination we've never achieved. The planetary defense grid. The blueprint exists. A next-generation planetary defense grid would place 8 infrared telescopes in solar orbit, positioned 60 degrees apart to eliminate blind spots. Paired with ground arrays, they'd catalog 99.7% of near-Earth objects down to 40 meters diameter within 12 years. Deflection infrastructure scales in tiers: kinetic interceptors for slow, predictable targets, laser ablation stations in high orbit for objects discovered late, vaporizing surface material to generate thrust, nuclear standoff devices as a final option, tested in deep space and held in ready reserve. None of this is theoretical. The physics works. Mission architectures have been drafted by ESA, NASA, and CNSA. What's missing is funding beyond conceptual studies and the political will to build systems that won't justify themselves for 200 years. We're talking about infrastructure on the scale of a moon program, sustained across centuries. The alternative is watching the sky and hoping probability favors us. The cost of building it is a fraction of the cost of not building it. The decade window. The Pan-STARRS successor network, paired with upgraded space-based infrared sensors, reaches operational threshold in 2031. Full Southern Hemisphere coverage adds another 3 years. Statistical models place the next Gliese 710 class encounter somewhere between 2087 and 2143, with a 68% confidence interval. That gives us a 56-year head start if the models hold. If the encounter arrives early, or if the object is darker than expected, that window collapses to 22 years. A gravitational tractor requires 15 years of continuous thrust to deflect a 10-kilometer object by a safe margin. A kinetic impactor can be built and deployed in 4 years, but it only works if the object is porous enough to absorb momentum without shattering. We won't know which profile we're facing until the object is inside Jupiter's orbit. By then, half our options are already off the table. But knowing when it's coming and being ready for it are two entirely different problems. The choice. The kinetic option is faster, cheaper, testable within a decade. It handles rubble piles and irregular bodies. But if the target is monolithic ice or dense iron, the impact fragments it into a shotgun blast we can't track or stop. The tractor avoids fragmentation entirely, applies force gently over years, works on anything with mass. It also costs $340 billion to deploy, requires ion thrusters we've only tested at small scale, and demands political commitment across multiple administrations. If the object arrives inside the 15-year window, the tractor becomes a monument to good intentions. If we build the impactor and the object turns out to be solid nickel iron, we've armed the threat instead of deflecting it. NASA's 2029 Planetary Defense Review recommended a hybrid approach. Congress funded 18% of it. The European Space Agency proposed a joint tractor prototype. It's been in Phase A study for 6 years. China is building a kinetic test vehicle in silence. No one's coordinating. We have to choose the architecture before we know what we're defending against, and the wrong choice doesn't just fail. It makes the problem worse. And then there's the question no one in the briefings wants to answer out loud. The unspoken risk. Every deflection scenario in the public models assumes the incoming object behaves like the asteroids and comets we've studied. It assumes a density between 0.5 and 8 grams per cubic centimeter, a velocity under 35 kilometers per second, a diameter we can measure months in advance. It assumes we've seen something like it before. Gliese 710's passage could eject objects from the Oort Cloud we've never catalogued. Fragments of disrupted protoplanets, iron cores from collisions billions of years old, bodies compressed under pressures we can't replicate in a lab. A 15-kilometer iron sphere, moving at 60 kilometers per second, carries kinetic energy equivalent to 2 million megatons. There's no deflection system on any drawing board that can handle that. The impact would vaporize the interceptor before momentum transfer begins. A tractor couldn't generate enough thrust. The math just stops working. The contingency plan for that scenario: according to a 2026 Jet Propulsion Laboratory white paper, is atmospheric and climatological modeling, not deflection, modeling. In other words, if we can't move it, we document what happens when it hits. The wider lens. So we know the threat is real, we know the timeline is measured in decades, maybe a century, and we know the tools we have today are not the tools we need. But this story isn't unique to HIP 85605. Every planetary system in the galaxy is embedded in the same churning field of stars, dark objects, and uncharted mass. The Milky Way moves, and we move with it. Which means the choice we're making right now, whether to catalogue the sky or look away, is the same choice every technological civilization eventually faces. You can't opt out of living in a dynamic galaxy. You either build the instruments to see what's coming, or you wait in the dark and hope the odds hold. There's no third option. We're still in the window where detection matters. That won't last forever. If this kind of deep dive into the forces shaping our survival keeps you thinking, hit subscribe. There's more coming.